Good evening, good evening, good evening, everyone. It is a brand new year and it is time to get to work. New thumbnails, same physics, same sound. Let's get to business. Tonight, we're going to look at factors affecting the resistance of a piece of wire. Three main factors. We need to be able to understand them and explain them in terms of the metallic bonding diagram. Then we're going to take a look at the three important equations that deal with energy in a circuit. They come from the basics of Ohm's law, but we're going to work our way through them. That's quite a bit to get through, so let's get to work. Now, what we want to start with is the basics of what metals look like inside. So what we need to do is we need to build ourselves our metallic bonding diagram. You should be familiar with this from at least your chemistry, if not your physics. Okay, so what we've got is we have a system of positive metal ions that are in some form of regular structure. We call this a lattice structure. Okay, they are arranged in a nice regular pattern. We're going to do it as rows, like this, with a bit of gap between them. Now this is insanely out of proportion in terms of what's going on. That will become important later, the fact that it's out of proportion, but it's a good start for now. So here we go, we've got our positive ions. Right? These are generally in the solid state. As a result, they have fixed positions, they are locked in place, and they may vibrate back and forwards about these fixed positions, but may not in fact travel wherever they please. Okay, this is a feature of solids, so they can go maybe backwards and forwards a little bit in that direction, or they can vibrate backwards and forwards towards that, but they can't really go outside this. So if I was to say, like, if this is my ion, then perhaps this zone here, if I fill this in nicely, is the zone that it can operate in. Okay, it can bounce around all over that. I hope that's okay. So let's move on. Why are we interested? Because most electricity takes place inside metals, and most electricity is carried by tiny little particles called electrons. Okay, electrons, or as we generally call them in electricity, charges, because they are moving charged particles, are going to travel from one end of your metal to the other end of your metal. That's what we do. So if we put a big enough negative charge up here and a big enough positive charge over here, then our electrons are going to be repelled from this end and travel towards this end. Okay, this is what we mean when we say there's a potential difference. Right, so the electron gets sent along here. Now, in an ideal world, our little electron picks up energy here because it's starting to move. It travels along, passing that energy from one electron to the next electron to the next electron in a nice little domino effect system that makes things go very rapidly, like we discussed pre-Christmas, that all the electrons move all at once. And this is great, except that sometimes it doesn't work. Sometimes this little electron is sitting like this. This one comes in, hits it, and this one goes, all right, I'm off, and then goes bang, and gets absolutely rammed into this ion. When that happens, the energy that was meant to be transferring all the way down to this other end of the diagram doesn't get that far. It gets sent into this ion. Okay, and it gets sent into it as movement energy because it's a collision. So it transfers movement energy into this. All right. That in turn means that I get less charges arriving at the other end every second. And less charges arriving equals less current. Because remember that current, I, is equal to the number of charges you get, Q, divided by the time it takes you to get them. So if I'm getting less charges, I'm going to get less current. Alright? Now that matters because of Ohm's law, that R equals V divided by I. So that's this equation. Now this is an inverse relationship, so pay attention. If the current goes down because it's on the bottom line of the equation, that means the resistance goes up, assuming that my voltage didn't change. Okay, so assuming I didn't change my battery or something like that, If my current goes down, my resistance goes up. Are we happy with that? Good. Now in this diagram it's pretty handy. We've only got 1, 2, 3, 4 rows of these things to get past. So most of my electrons are going to fly along here and get through this massive gap in the middle. The odd one's going to bounce in, and that's cool. Okay, and we'll be sending thousands upon millions upon trillions of electrons down here. So this is a pretty low resistance situation. So my question is, can I make the situation easier to get down? And can I make it more difficult to get down by changing the physical properties of my wire? And the answer is yes. On all counts, I can make it more difficult, and I can make it easier. Alright, so over we go then. Let's see how we make it more difficult. So let's imagine that I had a wire that looked like this. Okay, nice short piece of wire, and into that wire I'm going to put some positively charged ions. Now I'm not going to stick the positive charge in them, I'm just going to colour them in a kind of red colour, because black and white, gets a little bit boring on the screen. So we'll stick in, there's 3 of them. Okay, end to end, 1, 2, 3, 1, 2, and 3. Alright, and what I need to do is I need to get this little guy to go along here. Now bearing in mind, remember, they're not sitting where they are moving backwards and forwards, they're bouncing about a little bit, so we'll kind of jumble them up slightly in place. Okay, but they are moving kind of like that. Okay, so this guy's going to come along here and, oh, you made it. Yay! But equally, the next time one tries it, it can come in here and this could find that this is in this position and bang, doesn't make it. All right, and this becomes a probability game. It's a bit like throwing a dart at a board blindfolded. Right, if I have a board here and I fire darts at it blindfolded, you get this kind of random scatter shot effect. At some point, one of them is going to hit the bullseye. Right, that's going to happen at some point. You're going to get bang, one dead in the middle, which is good, I think. In this case, it's not though. If I'm trying to punch my electrons down through this and it hits the ion, I lose that one. Alright, so what are the chances of that happening? Well, here, it's roughly, let's imagine there's equal chance for everything, it's a 1 in 6. So let's imagine that I make the wire twice as long. Okay, make it 2 times as long. What happens to the chances of a collision? Well, the chances of a collision actually go up, right? Because I have to get past this pair, and then this pair, and then this pair, and I would have been free last time, but now I have to get past this pair, and this pair, and this pair. My chance of a collision doubles. And since we've got so many electrons coming along here, that means that the number of collisions actually doubles. Okay, it's not just a chance. When you're dealing with this many electrons, when the chance doubles, it does double. Okay, happy with that? So we now get double the number of collisions. That means we're going to get half the current. Okay, because we're now getting half as many electrons down through this as we did before, because we had twice as many collisions occurring. And because we've got half the current, we therefore have twice the resistance. Because remember, as the current goes down, the resistance goes up, but they are linked by an equation, so halving the current doubles the resistance. And this is the first thing I need you to learn then, that length of the wire is directly proportional to the resistance. Okay, and what this means is if you double the length equals double the resistance. And for triple award, you have to recognize as well that that means in terms of current, that if you double the length, that will equal half the current. Right? Double award, you're unlikely to get asked that. You might, but it's unlikely. Okay, so that's your learning point here for length of a wire. I don't want to labour that too long because we have more stuff to get onto. We've got 5 minutes left to do our next two. Next one up. What if, let's take a look at our wire as if we're looking down our wire like this. Okay, so let's see if we can get a 3D diagram going on here. Now, I will warn you, my art is terrible, in case you hadn't noticed that from the channel trailer. Right, so let's get ourselves a little. Right, there we go. That sort of looks like a wire. Ideally, I would like a curve. Let's just draw that. Save ourselves a time. Okay, that's awful, but it'll do. Okay, I hope you understand what we're doing here. We're looking along this wire. Okay, so inside our wire, we're going to have our ions, and they're going to be sitting, waiting for us. Like this. Okay? And what I need to do is I need to get my electrons. So let's get myself a little electron. I need to get it through here. Just go wham, in through there. Right, now hopefully it can find a little channel and fly down and go out there. Right, and it can go through here, and it can go through here, and it can go through here. Now the question becomes, what happens if I change the thickness of my wire? So let's get the exact same situation going on over here, but let's shrink down the thickness of my wire. Right? Now the good news is I'm going to have less ions, so that's good. Okay. The bad news is though that those less ions are still taking up space. And the question becomes, which would you rather try and fly down? Would you rather try and go down through here, or would you rather try and go down through here? Now I'm hoping the answer is obvious from my diagram, that this diagram here has, yes, it's got more ions, but it has more space in that one. Okay, there's much more empty space compared to ion space. If you were to do the ratio of them, this is like, 1, 2, 3, 4, 5 ions, but a huge, vast empty space. Remember from your chemistry, most of the atom is empty space. Okay, so yes, you're increasing the number of atoms, but you're vastly more increasing the empty space. Whereas in this one, you've got 3 atoms, or 3 ions, but you don't quite have the same proportionate size of empty space. So the thicker wire offers more paths for the electron, or whatever charge it happens to be that you're using, okay? For the electron or charge that you're using, okay? More paths equals less collisions, right? There's going to be less impact here. More electrons are going to get through this one here than are going to get through this one, okay? Less collisions equals more current. And from before then, that means that more current equals less resistance. And it gets better actually, because doubling the thickness not only doubles your space in that direction, but it also doubles your space in that direction. So it actually gives you 4 times the amount of current. Okay, because it's the area that matters, not the thickness. So the rule is this, that if the area is multiplied by 2, and by area we mean the cross-sectional area. Okay, so if we cut the wire down, if the area is multiplied by 2, the resistance is halved. If the thickness, and this is something that sneaky examiners do, ask what happens to the thickness. If the thickness is multiplied by 2, then the resistance is quartered. Okay, because increasing the thickness by a factor of 2 increases the area by a factor of 4, because you're increasing it in 2 directions. Happy? Good. Good. And then finally, our last one, the key one here is temperature. So on the temperature, We'll put a wee title up here. Temperature of the wire. Okay, with a minute or so to go on this one before we move on to the next thing. So the temperature of the wire, nice and straightforward. This one, temperature is kinetic energy. Right? When you're talking about something being warm, something being cold, you're actually talking about the kinetic energy of the particles within it. So if your wire is warm, then the particles within your wire, and that is the ions, are moving like crazy. Not only are they going fast, but they are also traveling a greater distance. Okay, so this one's moving, and they're moving really quickly, and you're trying to get an electron through this gap. Now if they're sat still, there's a gap. You can get through it. If they're going like bejesus like this, and the other one's doing the same, likelihood of your electron getting through here without at least losing some of its energy is pretty low. So the result is you're going to end up with a lot more collisions. So hotter wires mean more collisions. And I hope we can now fill in the rest of this almost automatically ourselves. Hotter wires, let's try to get the spelling right. Hotter wires, more collisions. More collisions means less current. Change the font. Less current means more resistance. Okay, not necessarily double in this case because it depends on which temperature scale you're using, but I have seen this asked as a question before. It's a sneaky question, so let's just have a little look at this. If this is temperature, and the temperature is in degrees Celsius, and we have resistance up the side, in whatever unit you want, probably ohms, then your graph should look something like this. Okay, it doesn't have to be a straight line, it just has to go up. But as the temperature increases, the resistance increases. But the important thing here is that at 0 degrees Celsius, it doesn't have no resistance. Okay, wires with ice on them still have resistance. So therefore, it's very, very important that if you're asked to draw this graph, you don't try and start it at 0, 0, you start it up here. And that's it. 3 factors that affect a wire. Length of a wire. Double the length, double the resistance. Thickness of the wire. Double the thickness, quarter the resistance, because it's actually the area. Right? And then temperature of the wire, as the temperature increases, the resistance increases. I'm just checking the chat here. Thomas Silk, yes, this is for triple award. I'll try and point out the differences for triple and double. All right, now moving on then. We've got to do our equations for energy and power. They're on the left hand side of the screen here. They are E equals ITV, P equals E over T, and P equals IV. Now they work exactly like Ohm's law, which is that they can be used for a whole circuit or part of a circuit. So let's just start with part of a circuit to start with. Do things nice and easily. So here we've got a resistor, and let's say our resistor is using 20 volts, right, and through it is flowing a current. So flowing this way is a current of let's say 0.5 amps. Right? And that's been going on for 1 minute. Okay, what I want to do is I want to know how much energy is being used and what's the power. Right, now the equation for energy is a little bit of a cheat. It comes from the definition of voltage, that voltage is equal to the amount of energy you give to a single coulomb of charge. So V equals E over Q. And the definition for current is I equals Q over T. Okay, we're going to draw it like that if that's okay. Which means that Q equals IT. Now if I substitute IT in here, I can write that V equals E over IT. Now if you're not following this, don't panic, but this is where it comes from. Multiplying both sides by IT gives me E equals ITV. So the energy equation simply comes from a combination of my voltage equation, my definition from voltage that we did a couple of episodes ago, and my definition for current. Okay, it's nothing special, but it is a useful thing to know. Now I'm going to get rid of that because it's on the left hand side of the screen and we want some real estate here. So I want to find my energy. So let's start with, what do we know? List what you know. I know that my voltage being used is 20. I know that my current I is 0.5. I know that my time t is equal to 1. Time is not measured in minutes. Nearly caught me, little examiner man, but you're going to have to get up pretty early in the AM to catch old Mr. Physics Rocks. So I know that it's 60. All right, watch out for that, 60 seconds. It's the only trick that can be pulled here. And then it's formula working answer unit. Energy equals current times time times voltage. I would sometimes say IVT because I'm old school, but ITV is a little bit easier to remember because of the TV channel. So current 0.5, time 60 times voltage 20, giving you a total energy of E equals 30 times 20, so that's 600. Okay, and 600, and because it's an energy and we're in physics and we have to be consistent, that energy is measured in joules. Nothing to it. All right, so what's the power? Well, remember way back in year 11, we had a general definition for power. The power is equal to work done divided by time taken. Work done over time. But work done was measured in joules. So work done was just a fancy way of saying energy. And our better way of writing this is actually power is equal to, in general, in all of physics, is equal to energy divided by time. Right? Now it doesn't matter what branch of physics you happen to be working in, this is true. Okay, your power is measured in watts. That's W. Your energy should be measured in joules. J. And your time should be measured in seconds. Yes. And there's only one exception to this, and we'll come to that in about a month's time, which is when you're doing domestic electricity, because the watt's quite a small unit, and we need something a bit bigger. But we'll deal with that when the time comes. All right. So let's work out what the power is. That if power is energy divided by time, then power P would be equal to E over T, which is our equation on the left hand side there. Just in general, it's energy over time. But we've just written that energy is ITV, so we can write that P equals ITV divided by T. And even the mathematically non-savvy amongst you should recognize that that's a multiply by T, that's a divide by T, so they just cancel each other out. And that gives you P equals IV, which is our third equation. And this is the most common equation that we use for when we're dealing with power. So let's pop back to our example and try and work out what is the power of this object. So the power is equal to IV, so P equals IV. So P equals, we've already listed our stuff, so it's 0.5 times 20. So P equals 10 watts. Now, what we sometimes use, or what the general kind of trick here is what does that mean? And this means 10 joules being used every second. All right, from that. And that's all there is to it. It just gets a little bit more complicated after that. So let's up the level a bit and see if we can't put it into a proper functional circuit. Oh, wrong button. So let's get ourselves a little power pack going on here. So there's a power pack, well, part of a power pack, not straight lines. Sorry for those of you who are a little bit anal about such things. Round we go, round we go, round we go, up here and across here. Oh, that's going to mess everybody up. Right, 2 resistors. So we'll pop one in there, pop one over there. And let's get some numbers. So what do we fancy for numbers? Let's go 20 ohms and we'll go 40 ohms. Keep things nice and simple in terms of splitting these things up. Hope so anyway. Spin that round. There we are. And let's give you a 12 volt power supply. Okay, so question 1 is, of course, what's the current? We can make this a 10 volt power supply. Try and keep the math simple. Alright, so what is the current coming out of this battery? So what we want to do is we want to use Ohm's law for the whole circuit. So that is between this point and this point. So Ohm's law from last time, for those of you who are, maybe a little bit suffering memory wise, V equals IR. For the whole circuit, the total voltage is 10, equals the current, which is what we're trying to find out, times the resistance of the whole circuit is 60. Okay, so much for keeping the math simple. So I equals 10 over 60, which is 1 over 6 amps. Now in a real exam, I would go and put that into my calculator and give myself a decimal answer, write down 1.67, but I'm not going to here because I haven't been asked for that. What we're trying to find out here is we're going to try and find the power of each resistor. Okay, that looks like a difficult question, but we've got 1/6 of an amp flowing around this each time, so that's good. We know that's going on. Now, because this is a series circuit, we've got 1/6 of an amp here, which means we've got 1/6 of an amp going through this. So we've got our current sorted out nicely. So that's 1 over 6 amps, and that's true over here as well. If that's not clear, would you pop a little comment at the bottom and let me know that that's not clear? I can spend a little bit more time in the next video explaining how these circuit systems work. Alright, now what we need to do is we need to find the voltages across each of these. We've got the current and we've got the resistance of each of them, so what we're going to do is we're going to use Ohm's law. We can do it by ratios. I don't really like that. Let's play with Ohm's law a little bit more. So let's use Ohm's law between here and here. That's the cool thing about Ohm's law, which is provided we pick 2 points, we're good. So on each side of that, we have that V equals IR. So V equals, the current is 1/6 of an amp, so that's 1 over 6, multiplied by the resistance, which is 20. So the voltage is equal to 20 over 6. God, I don't make life easy for myself, do I? So the voltage is equal to 20 over 6, so that's 3 and 2/6, which is 3 1/3, so that's 3.33 volts. I think. I hope so anyway, I'm doing this in my head. Right, over to the other side then. Using Ohm's law for the other resistors, so let's get ourselves a little circly thing and show you what we're using. So we're going between, let's go purple. So we're going between here and here. So from one side of our resistor to the other, we again use V equals IR. V equals the current, which was 1/6, multiplied by the resistance, which is 40. So that should give me a voltage of equal to 6.67 volts. Right, and I know I'm right because if I take these two voltages, 6.67 and 3.33, and I add them together, I get 10 volts, which is what came out of the battery in the first place. That's great. Okay, so that's lovely. We've got our voltages on here as well. So let's write these in. So this is 3.33 volts, and this is 6.67 volts. And I strongly recommend you do this in the exam. Like, as you find stuff out, pop it onto your diagram. You're not getting any marks for it, but it makes life a little bit easier. So what's the question? I want the power of each resistor. So let's take the 20 ohm resistor first. So 20 ohm resistor. Now notice that how I'm laying this out. I've been doing this probably for longer than most of you have been alive, but I still write down what I'm doing, where I'm going, because I need people to understand what I'm at. So for the 20 ohm resistor, we want P equals IV. So P equals, but what's the current through my 20 ohm resistor? Look, I've put it on my diagram because I'm a clever boy. So I is 1 over 6 multiplied by 3.33 recurring. Okay, so I have really messed up on that one, but that's okay, we'll get this sorted out. So grabbing the calculator from the drawer, we get P equals 3.3, or not, 1 over 6, so grab your calculators everybody, multiply that by 3.33, and that gives me a power of 0.555, all recurring, so we'll call that 0.56 watts. Alright, now what do you think happens to the next one? Okay, we want our 40 ohm resistor, and again, let's not get lazy. We're down to a minute left on the show, but no excuse for bad manners when it comes to writing. So 40 ohms. Apologies for the occasional W there. It's that W is the shortcut for ohms on symbol. So 40 ohm resistor gives me P equals IV. So P equals the current, which again was 1/6 multiplied by 40. So that should be twice that, but we're still going to grab our calculator because we're in an exam. We accept the fact that we might have messed up, we might have made a mistake, and there's no point doing an unnecessary error carried forward. So 1/6 times not 40, that's the voltage. See, it happens. Okay, my voltage was 6.67. It happens under pressure for time. Bad things happen. Good job, I caught that. Okay, and that gives me 1.11111, so we'll leave that as 1.11 watts. Twice the power, takes twice the amount of energy per second to get through the 40 ohm resistor. That's what it's about. Okay, that's what we mean by resistance. It takes twice as much energy to get through it. We're losing twice as much energy every single second. This is what the power rating is about. Alright, ladies and gentlemen, that was a lot. In the description below, there's a link, very short worksheet this week, but do go and practice these things, practice these equations, try your best to do the explanations, and it makes a difference. Hit me up with a comment. If you can't do any of the questions, I'll go through it next time if needs be, but do practice this. It's one thing to listen, it's another thing to do. Thank you so much for tuning in tonight. It's great to see you back. I'm looking forward to a good year in this. Year 11's next week because you guys have an exam potentially coming up very, very soon. So we're going to hit some serious revision for you guys. So thank you again. And all that remains to be said is don't forget, physics rocks. It's true. And a shout out to Finn.